Assalamualaikum warahmatullahi wabarakatuh, and a very good day to all the students. So again, we come back to DRM1413 Manufacturing Technology for diploma students. Today we're going to look at on the new chapter, which is rapid prototyping. So for today's topic, we are going to look at on the introduction for rapid prototyping. And number two, we're going to look at on the additive processes under RP, as well as its application for RP itself. So rapid prototyping or RP is a family of fabrication methods to make engineering prototypes in minimum possible lead times based on a computer-aided design CAD model of the item. The traditional method of fabricating a prototype part is machining, which can require significant lead times up to several weeks, sometimes longer, depending on part complexity, difficulty in ordering materials, and scheduling production equipment. A number of RP techniques are now available that allow a part to be produced in hours or days rather than weeks, given that computer model of the part has been generated on a CAD system. Special need that motivates the variety of RP technologies arises because product designers would like to have a physical model of a new part or product design rather than a computer model or line drawing. The creation of a prototype is an integral step in the design procedure. A virtual prototype, which is a computer model of the part design on the CAD system, may not be adequate for the designer to visualize the part. It certainly is not sufficient to conduct real physical tests on the part, although it is possible to perform simulated tests by finite element analysis or other methods. Using one of the available RP technologies, a solid physical part can be created in a relatively short time. The designer can therefore visually examine and physically feel the part and begin to perform tests and experiments to assess its merits and shortcomings. Available RP technologies can be divided into two basic categories. Number one is material removal process, and number two is material addition process. The material removal RP alternative involves machining, primarily milling and drilling using a dedicated computer numerical control (CNC) machine that is available to the design department on short notice. To use the CNC part program, a part program must be prepared from CAD model. The starting material is often in a solid block of wax, which is very easy to machine, and the part and chips can be melted and re-solidified for reuse when the current prototype is no longer needed. Other starting materials can also be used, such as wood, plastics, or metals. The CNC machines used for rapid prototyping are often small, and the terms desktop milling or desktop machining are sometimes used for this technology. The principal emphasis in this topic on material addition RP technologies, of all which work by adding layers of material one at a time to build a solid part from bottom to the top. Starting materials include number one, liquid monomers that are cured by layering into solid polymers, and number two, powders that are aggregated and bonded layer by layer, and number three, solid sheets that are laminated to create the solid part. In addition to starting material, what distinguishes the various material addition RP technologies in the method of building and adding material are the deposits of a soft plastic filament in the outline of each layer, while others bond solid layers together. There is a correlation between the starting material and the part building techniques. as we shall see in these RP technologies. The common approach to prepare the control instruction in all of the current material RP, addition RP techniques involve the following steps. Number one, geometric modeling. This consists of modeling the component on a CAD system to define its enclosed volume. Solid modeling is the preferred technique because it provides a complete and ambiguous mathematical representation of the geometry. For rapid prototyping, the important issue is to distinguish the interior of the part from its exterior, and solid modeling provides for this distinction. Number two is a tessellation of the geometry model. In this step, the CAD model is converted into a format that approximates its surfaces by triangle or polygons, with their vertices arranged to distinguish the object's interior from its exterior. The common tessellation format used in rapid prototyping is STL, which has become the de facto standard input format for nearly all RP systems. Number three is slicing of the model into layers. In this step, the model in STL file format is sliced into closely packed, closely spaced parallel horizontal layers. Conversion of a solid model into layers is illustrated in this figure here. These layers are actually subsequently used by the RP system to construct the physical model. By convention, the layers are formed in the XY plane orientation, and the layering procedure occurs in Z-axis direction. For each layer, a curing path is generated, which is called the STI file, which is the path that will be followed by the RP system to cure the layer. So as being explained to you just now in additive process, there are three types of additive material in RP, which is number one, liquid phase, number two, solid phase, and number three, powder based. We will discuss examples of each class in this following three section or three categories. So the starting materials in this technology is liquid. About a dozen RP technologies are in these categories, of which we have selected the following to describe. Number one is stereolithography. Number two, solid ground curing. And number three, droplet deposition manufacturing. So let's look at stereolithography or SLA. Well, stereolithography was the first material addition RP technology dating from about 1988 and introduced by 3D Systems, incorporated based on the work of inventor Charles Howe. There are more installations of stereolithography than other RP technology. Stereolithography is a process for fabricating a solid plastic part out of photosensitive liquid polymer using a directed laser beam to solidify the polymer. The general setup for process is illustrated in a figure number one and number two. And a part fabrication is accomplished as a series of layers in which one layer is added into the previous layer to gradually build the desired three-dimensional geometry. While the part fabricated by SLA is illustrated in here. So the SLA apparatus consists of number one, platform that can be moved vertically inside a vessel containing photosensitive polymer. Number two, a laser whose beam can be controlled in XY direction. At the start of the process, the platform is positioned vertically near the surface of the liquid photopolymer, and a laser beam is directed through a curing path that comprises an area corresponding to the base of the part. This and subsequent curing paths are defined by STI file. The action of the laser is to harden the photosensitive polymer where the beam strikes the liquid, forming a solid layer of plastic that adheres to the platform. When the initial layer is completed, the platform is lowered by a distance equal to the layer thickness, and a second layer is formed on top of the first by the laser, and so on and so forth. Before each layer is cured, a wiper blade is passed over a viscous liquid resin to ensure that its level is the same throughout the surface. Each layer consists of its own area shape, so that the succession of layer one on top of previous creates the solid part shape. Um, so photopolymers are typically acrylic, although use of epoxy for STL has also been reported. Sorry. And after all the layers have been formed, the photopolymer is about 95% cured. The piece is therefore baked in a fluorescent oven to completely solidify the polymer. Excess polymer is removed with alcohol, and light sanding is sometimes used to improve smoothness and appearance. Depending on its design and orientation, part may contain overhanging features that have no means of support during the bottom-up approach used in stereolithography. Mm. Okay, so now let's look at second types of liquid-based rapid prototyping, which is solid ground curing, or SGC. Well, like SLA, SGC works by curing a photosensitive polymer layer by layer to create a solid model based on CAD geometry data. Instead of using a scanning laser beam to accomplish the curing of a given layer, the entire layer is exposed to an ultraviolet light source through a mask that is positioned above the surface of the liquid polymer. The hardening process takes 2 to 3 seconds for each layer. The SGC systems are sold under the same Solidus system by Cubital Ltd. The starting the starting data in SGC is similar to that used in stereolithography. A CAD geometry model of the part has been sliced into layers. For each layer, a step mark for each layer, the step-by-step procedure in SGC is illustrated in this figure and described as like, okay, number one, a mask. A mask is created on a glass plate by electrostatically charging a negative image of the layer onto the surface. The imagining technology is basically the same as that used in photocopiers. Number two, a thin flat layer of liquid photopolymers is distributed over the surface of the work platform. Number three, the mask is positioned above the liquid polymer surface and exposed by a high-powered ultraviolet lamp. The portions of the liquid polymer layer that are unprotected by the mask are solidified in about 2 seconds. The shaded areas of the layer remain in the liquid state. Number four, the mask is removed, the glass plate is cleaned and made ready for subsequent layer in step one. Meanwhile, the liquid polymer remaining on surface is removed in a whipping and vacuuming procedure. Number five, the now open areas of the layer are filled with hot wax. When hardened, the wax acts to support overhanging sections of the part. And number six, when the wax has cooled and solidified, the polymer wax surface is milled to form a flat layer of a specified thickness, ready to receive the next application of liquid photopolymer in step two. Although we have described SDC as a sequential process, certain steps are accomplished in parallel. Specifically, the mask preparation step 1 for the next layer is performed simultaneously with the layer fabrication step 2 through 6 using two glass plates during alternating layers. The sequence for each layers will take about will take about 90 seconds. Throughput time to produce a part by SDC is claimed to be about 8 times faster than competing RP system. And number 3 is droplet deposition manufacturing. This system operates by melting the starting material and shooting small droplets onto a previously formed layer, the liquid droplet. Droplets cooled well on the surface to form new layer. The deposition of droplets for each layer is controlled by moving XY spray nozzle workhead, whose path is based on a cross-section of a CAD geometry model that has been sliced into layers. After each layer has been applied, the platform supporting the part is lowered a certain distance corresponding to the layer thickness in preparation for the next layer. The terms droplet deposition manufacturing DDM refers to the fact that small particles of work materials are deposited as projectile droplets from the workhead nozzle. Several commercial RP systems are based on this general operating principle, the differences being in the types of material that is deposited on the corresponding technique by which the workhead operates to melt and apply the material. An important criterion that must be satisfied by the starting material is that it be readily melted and solidified. Work material used in DDM include wax and thermoplastics. Metals with low melting points such as zinc, tin, lead, aluminum has also been tested. The common features in RP system is that the starting material is solid. In this section, in this slide, we will discuss two solid RP system, which is number 1, laminated object manufacturing, LOM, and number 2 is fused deposition modeling, FDM. So now let's look at the first one, which is laminated object manufacturing, or LOM. The principal company offering laminated object LOM system is Hillis Incorporation, of which interest is that much of the early research and development work on LOM was funded by National Science Foundation. And the first commercial LOM unit was shipped in 1991. Laminated object manufacturing, LOM, produces a solid physical model by stacking layers of sheet stock that are each cut to an outline corresponding to the cross-sectional shape of CAD model that has been sliced into layers. The layers are bonded on one top of the previous one before cutting. After cutting, the excess material in the layer remains in place to support the part during building. The starting material in LOM can be virtually any material in sheet stock form, such as paper, plastic, cellulose, metals, or fiber reinforced materials. The preparation phase in LOM consists of slicing the geometry model using the STL file for the given part. And the slicing function is accomplished by LOM Slice, the special software used in LOM. Slicing the STL model in LOM is performed after each layer has been physically completed and the vertical height of the part has been measured. This provides a feedback correction to account for the actual thickness of the sheet stock being used, a feature unavailable on most other RP systems. With reference to this figure on your right hand side, the LOM process has each layer can be described as follows: picking up the section with a sheet of stock in place and bonded to previous leg. Number 1, LOM Slice computes which is the software computes the cross-sectional perimeter for the STL model based on the measured height of the physical part that current layer of completion. Number two, um, sorry. Number two, laser beam is used to cut along the perimeter as well as to cross-hatch the exterior portions of the sheets for subsequent removal. The layer is typically a 25 or 50 watt CO2 laser. The cutting trajectory is controlled by means of an XY positioning system. The cutting depth is controlled so that only the top layer is cut. Number three, the platform holding the stack is lowered and the sheet stock is advanced between supply roll and take out spool for the next layer. The platform is then raised to a height consistent with the stock thickness, and heated roller moves across the new layer to bond it to the previous layer. The height of the physical stack is measured in preparation for the next slicing computation by LOM slice software. When all the layers are completed, the new part is separated from the external material using hammer, putting knives and wood carving tools. The part can then be sanded to smooth and blended the layer edges. A sealing application is recommended using urethane, epoxy or other polymer spray to prevent moisture absorption and damage. Number two is solid base. Number two is fusion deposition modeling, or FDM. FDM is RP process in which a filament or wax or polymer is extruded into the existing part surface from a workhead or a workhead to complete each new layer. The workhead is controlled in XY plane during each layer and then moves up by distance equal to one layer in the Z direction. The starting materials is a solid filament fed from spool into workhead that heats the materials around 0.5 degrees C above its melting point before extruding it into the part surface. FDM was developed by Strata System Incorporation, which sold its first machine in 1990. And so the illustration for the FDM process can be seen in this figure here. So now let's look at on the common feature of RP technologies, which includes number one, selective laser sintering, and number two, 3D printing, three-dimensional printing. So selective laser sintering, or SLS, uses a moving laser beam to sinter heat fusible powders in areas corresponding to the CAD geometry model, one layer at a time, to build a solid part. After each layer is completed, a new layer of loose powders is spread across the surface using a counter-rotating roller. The powders are preheated to just below their melting point to facilitate bonding and reduce distortion. Layer by layer, these powders are gradually bonded into solid mass that forms the 3D part geometry. In areas not sintered by the laser beam, the powders remain loose so they can be poured out of the completed part. Meanwhile, they serve to support the solid regions of the part as fabrication process. SLS is actually a more versatile process than SLA or serial lithography in terms of possible work materials. Current materials used in selective laser sintering include polyvinyl chloride, polycarbonate, polyester, polyethylene, ABS, nylon, and investment casting wax. These materials are less expensive, than photosensitive resins used in stereolithography. They are also non-toxic and can be sintered using low powder CO2 lasers. Okay, now let's look at on 3D printing. This RP technology was developed in Massachusetts, in MIT, Massachusetts Institute of Technology, MIT. 3D builds the part in the usual layer by layer fashion using inkjet printer to eject and adhesive bonding materials onto successive layers of powder. The binder is deposited in areas corresponding to the cross sections of the solid part as determined by slicing CAD geometry model into layers. The binder holds the powders together to form the solid part while the unbonded powders remaining loose to be removed. While the loose powders are in place during the build process, they provide support for overhanging and fragile features of the part. When the build process is completed, the part is heat treated to strengthen the bonding, followed by removal of the loose powder. To further strengthen the part, a sintering step can be applied to bond the individual powders. The part is built on platform whose is controlled by piston. Let us describe the process for one cross section with reference to this figure here. Number one, a layer of powder is spread on the existing part in process. Number two, an inkjet printing head moves across the surface, ejecting droplets of binder on those regions that are to become the solid part. And number three, when the printing of the current layer is completed, the piston lowers the platform for the next layer. Starting materials in 3D printing are powders of ceramic, metals, ceramic, and binders that are polymeric or colloidal silica or silicon carbide. So that's it for 3D printing. So now let's look at on the application of prototypes, which includes its design, number two, engineering analysis and planning, as well as tools and manufacturing. As for the design in rapid prototyping, that was the initial application area for RP system. Designers are able to confirm the design by building a real physical model in minimum time using RP. The features and functions of the part can be communicated to others more easily using physical model than by paper drawing or displaying it on CAD system monitor. Benefits to design attributed to rapid prototyping include number one, reduced lead times to produce prototype components. Number two, improve ability to visualize the part geometry because of its physical existence. And number three, earlier detection and reduction of design errors. And number four, increased capability to compute mass properties of components and assembly. In terms of engineering analysis and planning, the existence of an RP fabricated part allows for certain types of engineering analysis and planning activities to be completed that would be more difficult without the physical entity. Some of the possibilities are, number one, comparison of different shapes and styles to optimize aesthetic appeal of the part. Number two, analysis of fluid flow through different orifice designs in valves fabricated by RP. Number three, wind tunnel testing of different streamline shapes using physical models created by RP. Number four, stress analysis of a physical model. Number five, fabrication of pre-production parts by RP as an aid in process planning and tool design. Number six, combining medical imaging technologies such as magnetic resonance imaging (MRI) with RP to create models for doctors in planning surgical procedures or fabricating prostheses or implants. In terms of toolings and manufacturing, the trend in RP applications is towards its greater use in the fabrication of production tooling and for actual manufacture of parts. When RP is adopted to fabricate production tooling, the term rapid tool making (RTM) is often used. RTM RTM applications divide into two approaches, which is indirect RTM method, in which a pattern is created by RP and the pattern is used to fabricate the tool. And number two is direct RTM, in which RP is used to make the tool itself. For example, for indirect RTM, number one, use of RP fabricated part as the master in making silicon rubber mold that is subsequently used as a production mold. Number two, RP patterns to make the sand molds in sand casting. Number three, fabrication of patterns of low melting points in limited quantities for investment casting. And number four, making electrodes for EDM. Examples of direct RTM includes number one, RP fabricated mold cavity inserts that can be sprayed with metal to produce injection molds for limited quantity of production plastic parts. And number two, 3D printing to create a die geometry in which metallic powders followed by sintering and infiltration to complete the fabrication of the die. Well, somehow, not all RP technologies can be used for all of these tooling and manufacturing examples. Interested readers should consult more complete treatments of the RP technologies for specific details on this and other examples as well. And last but not least, let's look at on problems with rapid prototyping. Principal problems with current RP technologies include part accuracy, number two, limited variety of materials, and number three, mechanical performance of the fabricated part. Several sources of error limit parts accuracy in RP systems include mathematical, process-related, and or material-related. Mathematical errors include approximations of part surfaces used in RP preparation and differences between the slicing thicknesses and actual layer thicknesses in physical part. The latter differences result in z-axis dimensional errors. And an inherent limitation in physical parts is that steps between layers, especially as layer thickness is increased, resulting in staircase appearance for sloping part surface. Process-related errors are those that result from the particular part building technology are used in RP system. These errors degrade the shape of each layer as well as the registration between adjacent layers. Process errors can also affect the z-axis dimension. Finally, material-related errors include shrinkage and distortion. And an allowance for shrinkage can be made by enlarging the CAD model of the part based on a previous experience with the process and materials. Current RP systems are limited in variety of materials they can process. For example, the most RP technology like SLA or stereolithography is limited to photosensitive polymers. In general, the materials used in RP systems are not as strong as the production part that will be produced in actual product. This limits the mechanical performance of the prototypes and the amount of realistic testing that can be done to verify the design during product development. So I think that would be all for today's topic, which is rapid prototyping. So we are going to look at on the new chapter in the next class. So for this topic, you can do some exercises to make you understand better. But somehow you don't have to submit it at the end of this lecture. But you can submit together with the other exercises at the end of this semester. With that, I thank you very much for your kind attention and time. So have a nice day and see you again in the next lecture. Bye.